Now we do. Perfect. Yeah.
Okay,
Okay.
sir. Am I
Yeah.
audible, sir?
Yes, we can hear you clearly as well. Yeah. Thank
Okay, okay,
you.
yes.
Okay. Great.
Then I'll stop sharing.
Yes, please. Yeah. Okay, Shankar, so I'll hand it over to you. Just two comments. The two of the talks, one by Pooja Devi and the next one by Souvik Roy, are going to be played via YouTube. So that we'll be able to take care of. Santosh would be playing those. Okay, so
Okay, good.
over to you, Shankar. Yeah.
Okay, thank you. Thank you. Welcome all. I'll just start the session. It is 1:29. I'll start now so that we can actually start this actual presentation by 1:30. There is six talks today. All are 15 minutes. So what I will do is I will give you a warning at the end of 10 minutes so that you can wrap it up in another 2 to 3 minutes so that we have time for 1 or 2 minutes for question and answer. So the first presentation is from Durgesh Tripathi on a unified scenario for the heating of the corona in quiet sun. Durgesh, you can start your presentation.
Let me share, Sankar. Thank you.
Yes.
Can you see my slides?
Yes. You can go to the slideshow mode. Okay, good. Go ahead.
Okay, all right. I just finished writing my talk. Thank you very much and good afternoon. And thank you for staying for this talk, although it's lunchtime, we realize, but I promise I won't take long. So this is a work done with my former master student who was also again in the JRF, V.N. Nived. Now he's a PhD student at ARMA and he was funded through my Max Planck partner group, which is in collaboration with Sami Solanki and his group at Max Planck. So I'll be mostly talking about data analysis from IRIS. And then at the end, I hope that I will convince you that the title I have given actually does represent the data, or the data rather represents the title. Okay, so as an introduction, you see you have coronal hole, quiet sun, and active region on X-ray images, and because it's hotter, you see that in X-ray and in extreme ultraviolet. Quiet sun is sort of omnipresent, whereas active regions are a function of solar activity. Whereas coronal holes during the solar minimum, they are mostly located at the poles. But when you go towards the solar activity maximum, then you find coronal holes are spread all over the disk. And what we know is that there is a continuous outflow of particles in the interplanetary medium, which is called solar wind. And to try to put together like the coronal heating in active region, quiet sun, as well as in coronal holes, and then also combine that with the formation of solar wind is sort of a problem which people are trying to look into for decades now, and it has become one of the most stubborn, if I may say, problems in astrophysics. Now, coronal holes, if you look at different wavelength images. So here I have put together almost simultaneous images taken by AIA from all the way from photosphere up to upper corona. What you see that in 211, you see very distinct regions which are dark and they're called coronal holes. Now, if you go lower into the temperature, you see still these coronal holes are very nicely visible. You have this part here, which you see in 211, but you don't really see it in 193. Now, that can also take you to a definition of coronal hole. And 193 turns out to be one of the best suited regions for unambiguous identification of coronal hole. If you go much lower, even lower, 1600, which is a sort of transition region, and also it has photospheric continuum in it, and you do not see any signature of those coronal holes whatsoever. And similar is the case for 304, right? So they are at the base of the transition region in the upper chromosphere, if you like. And the story continues that in photosphere, all you see is sunspot, but no signature of coronal holes. And if you measure the magnetic field, you would not be able to say that this region is corresponding to coronal hole and the other is not. right? So visually, there is practically no difference in coronal holes and quartz sun when you look into observations in chromosphere and photosphere. And work was done. I forgot to put the reference here. It was Pradeep Kashyap, myself, and Sami Solanki and Hadi Peter at Max Planck. What we did that we looked at magnesium 2 lines observed by iris, and this is the region we look at in AIA, and that's the part which was rastered by iris. That's the magnetic field corresponding to this particular region. As you can see, there is almost no difference in the magnetic field. Now, if you take the iris images and you obtain images at K2 and K3, so this is K2V and K3, you essentially find visually no difference within quartz sun and coronal holes, right? If you just show this, you will not be able to distinguish. Whereas what we did was to look into regions with similar magnetic flux density, right? So what we do is we look at those pixels within some magnetic field bin, and we average out the intensities in those magnetic field bin. And if you look at K2 and K3, as you know that they are forming at 2 different heights, you see that as the magnetic flux density is increasing, the intensities are increasing, but also you find that the quartz sun has larger intensity than the coronal hole, which is not obvious when you look at these images. And similar thing you find at K3. K3 is forming a little higher up than K2 in the atmosphere. But if you look into the continuum, which is the wing, which is going far away into the continuum, you see almost no difference. And that is what your photosphere sort of regions are showing. So what we find is that there's a significant difference in the intensities in coronal holes and quartz sun for the regions with identical flux densities. Now, why it is important, I'm bringing out because this actually set the scene for the work we did later on. No such difference is seen in the wing. And this is very strong implication for sun climate modeling, because there you would have to measure the magnesium 2 index as a proxy. And if such things are changing, then you have to take magnetic flux into account and for giving the input. But then it also poses a question that where exactly the solar wind originate? Because if you already see the intensity lower, why the intensities are lower? We have not measured Doppler shift in this. And if you're interested, you should wait for IIA Solar Conference, where Vishal will be presenting a poster where we do have measured Doppler shift, and we get some intriguing signature in the Doppler shift as well. Now, this question has been asked many times, and it's a very important question to look at. And it was Sumer where they first found out, Hassler et al., that if you look into these networks and you look at the velocities, what you find that there is a strong upflow which are coming from these network regions. And that suggested that the solar wind is rooted. This is neon 8, so this is about 20 megameter height, and that is upper transition region or lower corona, if you like. Then Tu et al. Found that it originates between 5 and 20 megameter loops, and which is much below neon 8 line formation. Then Stuckey et al. Took many spectral lines and did a lot of characteristics. And what she found, he or she, I don't know. What they found was that the coronal holes were blue shifted with respect to the quartz sun, no absolute blue shift, but with respect to the quartz sun, they were red shifted. And the intensities were seen reduced only for the lines which are higher than that temperature. Now, in all these work, they essentially did not take into account that what sort of magnetic field configuration do they have, except here that you have a network region, or extrapolate it and what kind of magnetic funnel topology you are finding, right? So a detailed study with much higher resolution is required to understand the location where the solar wind might have begun. And none of these, as I mentioned already, looked at the flux densities while looking at the intensities in Doppler shift. What we do now is, because we have iris, we can look at silicon 4, which is forming much lower, much below the neon 8 line, and that falls into the range where 2 et al. 5 to 20 megameter, and combine that with line of sight magnetic field with HMI. So this is our data. We have looked at 3 data set. So we only 3 because we wanted to have the slit which is covering both coronal hole and quartz sun, because we did not want to have any sort of instrumental differences and all that, because these are very precise measurements, if you like. Here is the region from AIA. That's the field of view of the raster. We identify the coronal holes by these contour. This is an ATDN contour, and we obtain the magnesium silicon 4 intensity map for this particular region. And if I just show you this, if I show you this, you will certainly find out this coronal hole and quartzon, but in silicon 4, there is no way one can distinguish. And that's the intensity distribution. What you find is that the quartzon in the beginning, you have
Durgesh, sorry,
yeah?
your screen is frozen now. Your slides are not moving for us, at least for me. Is that the same with others? Yeah.
Yeah. I want to tell. Yeah.
Shankar. Okay. Yeah. So I don't know what to suggest. Maybe you can stop sharing and start again. Yeah.
Yeah, maybe I'll do that.
So go 2 slides back, actually.
Which slide did you see actually? Can you?
The network and the coronal hole. Like
Right.
network.
Yeah. The network at the top right corner. Yeah.
Okay. Can you see my slides now?
Not yet, but it is. No.
No.
It's a black screen. Was a black screen.
Okay, let me try that again. Yeah, thank you, June. Do you see the slides now?
No, for me it is still a black screen.
Not it.
Hey.
Okay. That is strange. Had not yet experienced that in this meeting.
You want to try PDF?
I can do that, but let me just, I have to convert it into PDF first.
Oh, I see.
This is happening somehow. Whew. Sorry about that.
Shankar, do you want to move to Bhuwan and come back to Durgesh? I know it's going to be crazy to split a talk into 2. But
on the chance, let me just try.
Yeah, sure. Go ahead. Yeah.
Then
Try one last time. Yeah. See.
do you see it now?
Yes.
Yes, finally. Yeah.
Okay, so maybe I'll not make it full screen, or maybe I should try. The full screen, do you see?
Yes.
Yeah, sure.
Okay, so this is the slide we left upon. So all I wanted to say was that these works were very interesting, very nice, but they had not looked into the strength of the magnetic field when they're looking at the Doppler shift as well as the intensities. We now can do that by using iris observations, which because good spatial resolution and HMI with magnetic field measurement. So these are data. We looked at 3 because I think I already explained that. You heard it. What I'm trying to make a point here is that
Durgesh, if you move to the next slide, it has not moved for us. Yeah.
Okay.
For me, it is blank screen.
Maybe start with the next slide. Unshare, start with the next slide and then go. Yeah.
Okay. Do you see my slide?
No.
Sankar, why don't you, it's a good time for me to break also. Why don't you start the other one and I'll get back?
Okay, sure.
Yeah.
Bhuwan, are you ready?
Yeah, I can start sharing. Yeah.
Sure. Go ahead.
So is that clear?
Yeah, we can see it.
Yeah, sure.
Go ahead. I'm not introducing, so to save some time. Okay.
I have 15 minutes. Yeah.
Yeah.
Good afternoon. Yeah, this is Bhuwan Joshi from Udaipur Solar Observatory, PRL. The title of my talk is this multi-wavelength study of a low intensity, long duration solar eruptive flare associated with type 1 solar radius storm. So basically, I'll be presenting the observations which we have taken from our own Udaipur-CALLISTO system. And we will compare that with the one taken from Solar Dynamics Observatory. The collaborators in this study are Prabir Ramit Bhattacharya, Kushagra, Divya Oberoi, and Christian Monestein. In fact, all the co-authors are the part of Udaipur Callisto team, and I will discuss this Callisto instrument in later my slides. So I think this introduction is not much needed here, but for the sake of completeness, I'll just introduce what flares are. So flares are basically transient explosive perturbations in the solar atmosphere, and a large flare can release energy in excess of 10 to power 32 arcs. So it's a huge amount of energy. It's an impulsive process, and the animation on your right shows one such event which we have captured in H-alpha filter. So H-alpha filter means the brightening that we see here originate in the chromospheric layer of the sun. So I'll not go into the detailed stuff. What I would like to tell here is that historically flares have been divided in two parts, confined flares and eruptive flares. In fact, this classification scheme is well consistent with the stellar observations as well. The role of reconnection has been recognized in flare because no other process can release huge amount of energy that we see during a flare and in a very impulsive manner. So the confined event, essentially they are non-eruptive ones, they occur low in the corona and they lack coronal mass ejections. So they are modeled in terms of single loop structure or compact loop structure with little large scale motion. So since there are no coronal mass ejection, so what it means is that there won't be any significant change in the overlying field system. On the other hand, the eruptive flares, they are also called long duration flares. They are very important for space weather perspective. They are associated with the disruption of large scale coronal loops, then their reformation, and they are associated with coronal mass ejections. At the source region, we do see filament eruptions, post-flare loop arcade, flare ribbons, and so on. So all these features, they form the basis of a standard flare model. So just to introduce the eruptive flare and their main observations, I would like to show this limb event, which is basically an M class, a large flare. So what do you see here is that a flare essentially has a loop top source, which is close to the coronal reconnection site. You can see a loop top source here in 6 to 12 keV X-ray images. And then you do see ribbon-like brightenings, two ribbon-like brightenings in the lower layer of the solar atmosphere. And during the impulsive phase, what we see that these ribbon structures, they emit in hard X-rays. So we have foot point emission, we have loop top emission. So essentially, these two things, they form the basis of the standard flare model. The event which I'm going to introduce here is a small event. It's a C-class event, and it occurred in 12734 in 2019 March. So please note that during this period, the solar activity was very, very low. So this actually helped us in the detection of the long duration of the gradual phase because the pre-flare background was at approximately A0 level. So the motivation behind this study comes from the observations from Udaipur Callisto system, which is operational since October 2018. So what you see here is the E-Callisto system. So the Callisto stands for compact, compound, astronomical, it's a compound, astronomical, low-cost, low-frequency instrument for spectroscopy and transportable observatory. And it's indeed a very compact instrument. You can see that there is a LPDA, log periodic dipole antenna, of length 3.63 meter, having 28 elements. Then we have a portable container here, which I am showing by the marker, by the laser pointer. And inside this container, we have a computer, we have a Callisto spectrograph, and we take observations throughout the day. And since October Flare, very long duration event. So you can see the gauge light curve here. The flare has two stages, S1 and S2. The important thing is that the stage S1 is radio quiet, while during the stage S2, we have radio observations. We have intense radio burst. So we wanted to know what is happening there. I mean, why the first phase is radio quiet and why we have intense radio emission during the second phase. And
Okay, I have lost Bhuvan's audio. How about
Yeah.
others?
Yeah, I too.
I too.
Yes.
Okay.
Even we lost the screen sharing.
Okay, the screen I can still see, but
I'm not able to hear.
yeah.
It'll be fun to mix and talk.
Yeah, yeah.
I'm ready to with my people if you want.
So we are having Durgesh Joshi talk.
Exactly, yeah.
Okay.
Okay.
yeah, Shankar.
Yes, Bhuwan.
Yeah, can you see my slides?
No, the screen sharing has gone away and we could not hear you for some time also. Yeah.
Okay. So let me share again. The internet was intermittent actually.
So yeah, now we can see. Yeah.
Yeah, now you can see. So from which slide should I start?
E-Callisto.
Here?
Yeah, this one was okay. Then you can go to the next one. Yeah.
Fine. So I described E-Callisto here. And then I described the radio observations. So
Yes.
the motivation behind the study was these unique observations. So there is a long duration event. It has two stages, S1 and S2. The stage S1 is radio quiet, while the stage S2 has intense radio emission. And if you convert the frequency of radio observations to the coronal heights using a coronal density model, then it comes out that the radio emission is originating in the height range of 1.1 solar radii to 1.5 solar radii. So, Shankar, is it fine now?
Yeah, we can see it. Good.
Yeah. So now we would like to show some details of the flare in multi-wavelength. So this is how the active region evolved, and our event occurred on 8th March 2019, and during which the magnetogram suggests a very dispersed kind of magnetic structure. And if you compare this with AIA images at 94 angstrom, then we find that this essentially suggests a twisted structure in the corona, which we call as coronal sigmoid. Okay, so coronal sigmoids are well understood and well studied in solar physics. They show more association with coronal mass ejection. So this S-shaped structure is a coronal sigmoid. And now if I play this movie, so now I'm playing the movie, and this movie suggests that during the course of this flare evolution, the brightening shifts from west part of the active region toward the east part. So there is a sequential eastward shift in the brightening. The eruption starts at the west part of the active region, and then slowly the brightening moves toward the eastern part of the active region. So this eastward shift can be seen very clearly from these still AIA 131 angstrom images. Now, coming to the chromospheric observations, if we compare the X-ray light curve with AIA 304 angstrom observations, then we can clearly see the same scenario. We have the development of the flare ribbons in the western part of the active region first, and then the brightening slowly moves toward the eastern part. And with the formation of ribbon structure, we also see the formation of post-flare arcades. And we have two sets of post-flare arcades, set 1 and set 2. The first set corresponds to the beginning of the ribbon brightenings, while the second stage suggests the westward development of the corresponding flare ribbons. So essentially, the long duration of the decay phase is because of the composite emission coming from the stage 1 and stage 2 of the loop arcade. Another important observations are here, which are from AIA 193 angstrom observations. So what we see is that we see two dimming regions, T1 and D2. The region D1 lies in the positive magnetic polarity. The region D2 lies in the negative magnetic polarity. The dimming regions are localized and stationary, and these kind of dimming regions are called core dimmings, which suggest that the two dimming regions, D1 and D2, they essentially mark the foot point of the erupted flux rope rooted at opposite magnetic polarity regions. Now coming back to the radio observations, so the stage 1, during which we have brightening in the western part of the active region, there are no radio emissions, while during the stage 2, when we have eastward shift in the brightening, we have the radio emission. So now what is happening on the sun? This we wanted to understand. So for that, first we have chosen two frequency bands here, a low frequency band and high frequency band. And then we did a correlation study of the flux in these two bands. And we found that the correlation is very good. It means the two band emissions are highly synchronized. When we did cross-correlation study, we found a time lag of 0.18 second, which is an order of magnitude less than what is expected for a type 3 radio burst. So it means that essentially there is no drift between the two frequency, and this vertical structure is essentially a type 1 radio storm. And these radio storms are not much studied. We have only a few papers on this type 1 noise storms associated with flares. When we compared our observations with the linear force-free modeling, we found that these red high-lying loops, the large-scale loops, they correspond to a height of 1.5 to 2 solar radii, and the type 1 radio storm comes from the trapped electrons inside these large-scale loop systems. So basically, what we propose is that the eruption proceeded in an asymmetrical manner. So this plot shows the decay index. Decay index is basically a measure of how the horizontal component of the magnetic field decays with height. And the theoretical studies suggest that the critical value for torus instability lies within the range of 1 to 1.5. And this red curve is the decay index curve for n is equal to 1.5. So essentially, the western part of the active region was susceptible for the eruption because of the torus instability. So the eruption begins here, and then it proceeds toward the eastwards direction. And so the eruption essentially goes on in a zipping like motion. And then at the central part of the sigmoid, the region is relatively stable. So the eruption also slowed down, and then again it proceeds toward the eastern part of the sigmoid. So what is happening is that the large scale loops at the western part, they will restructure continuously, while when the eruption will proceed toward the eastern part of the sigmoid, we will have a formation of stable large-scale loops following the eruption of the sigmoid. So this suggests, okay, so this suggests that why we do not have any type 1 emission during the phase 1, while during the phase 2, we have the type 1 emission. So here I summarize the observations. So our study is essentially motivated by the observations taken from Udaipur-Callisto system. And in this work, we report the type 1 radio storm associated with an eruptive flare, and which is relatively less studied topic in contemporary solar physics. The radio observations together with EUV and X-ray observations suggest a dual stage of energy release, both in terms of temporal aspects and spatial aspects. This is very interesting that the type 1 storm occurs during the stage 2 only, and this we explain in terms of the eastward shift of the magnetic reconnection site. This is very interesting that we have twin core dimming regions, which are formed in the opposite photospheric polarities, which suggest that the two dimming regions essentially mark the foot point of the single erupted flux row. So the decay index analysis and the eastward shift in the brightness suggests that the sigmoid flux row erupted in a zipping-like manner, in an asymmetrical way, and this happens because of as a result of the asymmetry in the overlying magnetic field confinement, and this we proved by the decay index analysis. Also, we found that there was continual restructuring of the overlying loops, which are rooted at the western part of the flare ribbons. So please note that in the western part of the flare ribbon, the emission during the stage 1 comes. So the continual restructuring will not allow trapping of electrons there. While in the eastern part, we do see the formation of stable large-scale loops when the whole flux row had moved beyond the higher corona. So because of that, there is a trapping of electrons associated with the large-scale loops of the western part of the flare ribbons. And this has essentially made difference for the origin of radio emission during the two phases. So thank you very much. I'll stop here.
Thanks, Bhuwan. So just open it up for quick questions, maybe 1 or 2 quick questions. If you have, you can raise your hand. Okay, I don't see anything, and I don't see anything in the chat also. Okay, thanks, Bhuwan. Then let's move on to Durgesh.
Yeah,
maybe you can try sharing it. Bhuwan, you can unshare your slide.
Sure.
For anybody to ask questions to Bhuwan, they can type it in the chat. Bhuwan will be there to answer.
Can you see my slide?
Yes. You can go ahead, Durgesh.
Okay. Thank you, Sankar.
Yeah, 5 minutes.
How much time I have?
5 minutes.
5 minutes. Okay, good. Right, so that's my end. No, let me, okay. So this is what I was presenting, and I wanted to make a point that they had not looked at magnetic field, and we have started looking at magnetic field, and these are the 3 data sets we have. So here what you see is the coronal hole identified in AIA, that is in silicon 4. There is essentially no difference. If you look at the intensity distribution, the quiet sun is at lower magnetic field. There's intensity. So there are peaking at a lower value, but then eventually overtaking the coronal hole values at larger intensities. If you look at the magnetic flux distribution, almost identical. Of course, there is a noise below 20 Gauss, so we've taken that out, and this is the absolute flux distribution. So if you look at the Doppler shift, again, this is the intensity distribution now by taking care of the magnetic flux. So you take magnetic flux within the coronal hole and within the quiet sun, and you sum over the intensities. What you find that the coronal holes, which is red, have less intensity, quiet sun has larger intensity. You see that the intensity is increasing with magnetic field, which is expected. But what you also see that the difference between the two is sort of seem to be indicating that the difference in intensities are also increasing when you go towards the higher magnetic flux values. Look at the Doppler shift. These are the distribution again in the quiet sun coronal hole. What you can see that the quiet sun, when you go towards the higher values of in the red shift, the quiet sun takes over the distribution here, whereas here there is a small bump. If you can figure out at lower values, coronal holes are dominating. And if you look at this again, similar as intensities, what you see overall, both quiet sun and coronal holes are redshifted, which is also very clear from the distribution. But what you also see that with increasing flux, the quiet sun is more redshifted, whereas coronal holes do not show such an increase in the redshift. Whereas in non-thermal velocities, the distribution as well as a function of flux density, we do not see any difference. Now, this is the overall characteristic you see in one data set. We looked at 3 and we found similar pattern. So in order to increase the SNR, we just combine all these 3 data sets, considering that all the quiet sun and coronal holes are the same regions anyways. And then we come up with this plot here. With that now combines all the data set. And you can see clearly the SNR has improved. This is the intensity, and the point I wanted to make here that the difference is increasing with increasing flux densities. You see it much clearer here now because we have more data. The statistics has improved. The distribution of the velocity shows the same thing as for one particular data set, again with a much better way, that everything is redshifted, both coronal hole and quiet sun. The coronal hole with respect to quiet sun is blue shifted, right? Because it's more towards the blue. Now, if you start looking at the red shifted pixels and blue shifted pixels, what you find that in the red shifted only, for the same flux density, the quiet sun is more red shifted, whereas than the coronal holes. But if you look at only blue shift here, what you find that the coronal holes are more blue shifted than the quiet sun, right? So this is the coronal hole is red, and it's also increasing. The blue shift is increasing when you increase the flux density. Again, non-thermal velocity are showing the same pattern. There is not much difference, albeit at these small flux densities here, which could be measurement or could be real, which we don't really see in very great detail. Now, so what? All these results, what we find, these results are already indicating in some way that since there is this increasing flux outflows with increasing flux density, that means that on the networks, you already start seeing the sources of the solar wind at a height where silicon 4 is forming. Our preliminary analysis shows that it is forming at around 7 to 8 megameter, which is much lower than 20 megameter at Leon 8, which was said by Hassler et al. Now, this is only for the solar wind, but now if we combine the results by Wiegel and Mansolanki, and that is based on the extrapolation of the field lines using potential fields in coronal hole and quiet sun, what they found was that the difference when you look into the corona, that why actually coronal holes are darker and quiet sun is bright, can all be explained just by taking the statistics of coronal loops or the number density of different kind of coronal loops. What they found was that the quiet sun have much higher density of longer loops, and coronal hole had a lot of open loops, but the low-lying loops, the number density both in coronal hole and quiet sun were similar. So what you're looking at, a population of loops which are low-lying, which are everywhere in the coronal hole as well as in quiet sun, whereas the longer loops are closed in the quiet sun, whereas in the coronal hole, they are open, right? And now if you think in terms of that, what might be happening at those foot points because of the braiding, for example, or the movements of the foot point, that these small scale field will reconnect among each other, but they will also reconnect in quiet sun with the longer closed field lines, whereas in the coronal hole, they will be reconnecting with open field lines, and those will be producing jets, which will be observed as blue shift in coronal holes because the field lines are open and jet can go along the field lines. Whereas in quiet sun, they will have to be reconnecting two closed field lines, and eventually all you will see is just plasma draining, and all will be just redshifted. Now, in this scenario, what one can envision, this is a figure I copied from Fisk and Casper, which is taken from very different physics, which also explains the switchback. But now you can imagine that this part, let's say if it's a quaternion, this part is coronal hole. Here you'll have a lot of open field in the coronal hole regions and a lot of closed fields low down. Whereas here you'll have a lot of longer closed field and smaller fields here. And the topology then you will be producing in quaternion will be closed field and closed field reconnecting, producing another closed field, whereas in coronal hole, closed field reconnecting with open field, producing these kind of kinks, which will be then ejecting within the heliosphere as coronal holes. And that will also, this paper also explain in a similar way that how they would see the switchback, and we see a direct signature in our data.
Yes, 2 more minutes.
Yeah, so that essentially is that we can combine these loop statistics and the observations in this, as well as observation by Hassler and Tu et al. And we can find that just the impulsive heating can explain both the formation of the solar wind in the coronal hole and the quaternion heating, because the mechanism and the physics is very similar. Now, another point I want to make is, like, if you think about the reconnection taking place between closed field lines and closed open field lines, the non-thermal velocities, because the loop population density is very similar, you will observe similar non-thermal velocities in both the regions. And that's what exactly our observation shows, that in the non-thermal velocities are very, very similar in both coronal hole as well as in quaternion. So with that, I thank you very much for your time. Thank you.
Okay, thanks, Durgesh. Any questions? Please raise your hand. Quick questions, please. Durgesh, I have one question. Are there any studies on temperature difference between these coronal holes and in the region of your observations, wherever you see the coronal hole switchbacks? Are there any temperature measurements? What type of temperatures you see in here?
Yeah, that's what we want to do. The thing is that temperature sensitive lines will give us that, but there are no such data. And we wanted to do that with AIA, because now we can take this intensity summed up, so we can bring in better signal to noise ratio, and we can do a DEM. And we want to see a distribution of that essentially. So that is our next plan to do this. And if I may mention that we're also working with Bhargav, Vishal is working on with Bhargav and myself to do a sort of simulation and forward modeling of these lines, and we see such kind of structures and plasma parameters. That's our annual goal.
Okay, thanks, Durgesh. If you can unshare your slide, let's move on to the next talk, which is Pooja Devi. Will be streamed through YouTube. Will be streamed by Santosh Jagade.
Just give me a minute.
Yeah. Those who have questions for Bhuwan and Durgesh, please write in chat. They'll be happy to answer.
So I'm just starting the video from the Pooja Devi.
Okay, go ahead.
Hello, I am Pooja Devi from Bhuwan University, Nainital. The topic of my talk is a variation of chromospheric features as a function of latitude and time using calcium gas spectroheliograms for solar cycle 15 to 23. This work is done with Jagdev Singh, Ramesh Chandra, Muthu, Priyal and Ritika Joshi. So let's begin with a small introduction. Stars are the bright region near the sunspot with the magnetic field ranges from 100 to 200 Gauss. And networks are also the bright regions which outline the supergranules or large convective cells. Their magnetic field is less than that of the plasmas. Both plasma and networks are the bright regions, means both host bright features. But plasmas have higher density, are larger in size, and are brighter than that of networks. Also, both plasmas and networks are related to magnetic field, so they vary with the 11-year solar cycle. Now, let's talk about the subdivided chromospheric features which are used in this study. These features are enhanced network, active network, and quiet network. We can define the enhanced network as the decaying plages or the plage fragments into smaller regions when they decay as magnetic field weakens. These fragmented regions are identified as enhanced network with average intensity less than that of plage regions. And active networks are the bright uh, are active networks are less bright than the enhanced network and probably represent magnetic elements in the lanes between granules. They can also be associated with decaying plages or some magnetic elements seen at the photospheric layers. Now, the quiet networks are generally found at the boundary of large convective cells. The horizontal flow from the center of the cell carries the flux tube and deposit at the boundary of uh, cell, creating the increase in the magnetic field at the boundary, which causes increase in the brightness of these regions and appearance of quiet networks. Now, for the data analysis, for current studies, we take the data of Kodaikanal Observatory in calcium K wavelength from 1913 to 2004, which covers solar cycle 15 to 23. The chromospheric features are identified by putting a threshold value, which is done by Priyal et al. 2019. These are the threshold value for the identification of these features. After the identification of these features, the data is divided into heliographic latitude zones with an interval of 10 degree. And to reduce the scattering, the data we take monthly averaged data and which is further smooth over which is further smooth by taking running average over 1 year up to 40 degree and over 3 years for greater than 40 degree latitude belt. Now, variation in the plage area with latitude and time is shown in this figure. The red and blue curves correspond to northern and southern hemisphere respectively. From the figure, we see that the plages mostly occur up to 40 degree latitude belts, and after that, the occurrence of plages is negligible, which is expected. And the occurrence of plages is found maximum in 10 to 20 degree latitude belt, and in each latitude belt where it is visible, it is seen that the plage area show an 11-year periodicity. Now the dashed and solid line represent the peak of plage area in 30 to 40 degree latitude belt. We take 30 to 40 degree latitude belt because the activity starts at this belt and then move towards the equator. That is seen more clearly uh, by comparing the peaks with these solid and dashed lines. And also the activity in 30 to 40 remains for short duration, and it remains for longer duration as we move towards the equator. For the enhanced network, the fractional area is less than as compared to that of the plages, and it also the 11-year periodic variation. Similar to plages, the enhanced network are also found more around 10 to 20 degree latitude belts and the other latitude belts. And just like plages, as we move towards the pole from mid-latitude, the area of enhanced network is also decreasing, taking its minimum around 50 degree. But unlike plages, it again enhanced at the 62 limb. This is because the networks show colloidal fields, colloidal magnetic fields. But in the figure, we see that the northern hemisphere show enhancement, but southern does not show. This may be real or maybe some instrumental effect. And the 11-year cyclic variation shown by northern hemisphere in 60 degree to limb latitude is out of phase with that of the mid latitude belt. Now, variation in an enhanced network area is similar to those is similar to that of this is variation in a variation of active network area is similar to enhanced network area, but the active network area is found more than the enhanced network by a factor of about 2. It also saw an 11-year periodicity cycle, 11-year periodic cycle, just as enhanced network. And for the polar latitude, the cyclic variation is not clear after 1974. This is because after 1974 we have less number of data per year, which is also with frequent gaps. So just like enhanced network, the variation in 62 limb is out of phase with the variation at mid latitude belts. Similar to this, we have seen the long-term variation of quiet network areas also with the latitude and as a function of time. It also saw 11-year cycle, just like enhanced network and active network. But we see that the fractional area of quiet network is more than that of Plage's enhanced network and active network. It means that even though the quiet network is not directly related with solar activity, but it plays some role in increasing the magnetic field at the boundary of supergranules, which cause the increase in fractional area of quiet network. Now, to see which feature takes its maximum activity in which latitude belts, maximum or minimum in which latitude belt, we have created this table. This table shows the average amplitude variation of chromospheric features. The average is taken for the whole data, that is from solar cycle 15 to 23. From this table, we conclude that the activity in each of these features peaks around 20 degree and takes its minimum around 50 degree latitude belt in both northern and southern hemispheres. Now, the cross correlation coefficient as a function of phase difference is shown in this figure for Plage area. For our convenience, we have written middle value, means 5 for 0 to 10, 15 for 10 to 20, 25 for 20 to 30, and so on. And N and S represent the northern and southern hemisphere respectively. So from panel A, we see that as we move towards the equator, means from mid latitude towards the equator, the cross correlation coefficient is decreasing and the phase difference is increasing, as this is with the 35 degree latitude belts. The same result is shown by southern hemisphere also. If we come in panel C, we see that 45 and latitude belt show a negative phase difference with 35 and latitude belt. This means that the activity begins at 35 degree earlier and then move towards the 45 degree belt. Also, the cross correlation curve for 55 degree and 75 degrees, so minor correlation. The phase lag of 55N and the 55N, this is yellow one, and the 75N, this red one, do not show a good correlation and good correlation with 35 degree belt, but 55S in southern hemisphere, it show a phase difference of approximately 14 months, and 75 degree belt also 75S belt show double peak in the cross correlation coefficient as a function of phase difference, and these peaks are separated by 11 years. This may be due to the reason that the Plages are not present at higher latitude belts towards the poles. Now, cross correlation function of enhanced network and active network also show the same behavior for the latitude belt up to 45 degree, and but for the polar latitude belts, means 55 degree and 75 degree, they somewhat differ from the Plages. The cross correlation curves for 55 degree and 75 degree in both EN, means enhanced network, and active network showed two peaks around zero phase for 55N, 75N, and 75S in both of these features, whereas 55S show single peak only. The cross correlation curve for quiet network is similar to the other features at lower latitudes, but unlike enhanced network and active network, the cross correlation curve for 55S, uh, uh, 55N, and 75S show single peak in the quiet network. So this is the a table showing maximum cross correlation coefficient and phase difference in month. We from the table we get to know that the activity is not activity do not move from mid to equator uniformly. Means, for example, if we take the example of enhanced network, the activity or the phase difference between 25 and 35 is approximately 3, which increases to 11 and further increases to 32 months as the enhanced network moves from mid-latitude towards the equator. This behavior indicates that the activity does not shift at a uniform speed from mid to equatorial latitude belt, but it shifts faster at the beginning and slows down as it moves towards the equator. So these are discussion and summary. The variation of studied chromospheric feature is seen to follow 11-year periodicity cycle for each chromospheric feature and in both northern and southern hemispheres. The variation of fractional area of plages and networks with time are maximum around 20 degree and minimum around 50 degree latitude belt, which are consistent with Priyal et al. And Sindhuja et al. The enhanced network and active network variation show a sudden enhancement at the polar latitudes, that is greater than 60 degree, which is anti-correlated with the variation at 30 to 40 degree latitude belts. The cross correlation curves of enhanced network and active network indicate the significance existence of small scale magnetic element at the polar region. We found the toroidal field, that is plages, takes about 30 months to travel from mid latitude to the equator in both hemispheres. On the basis of phase difference, we found that the shift in the activity from mid to lower latitude belt is not exactly symmetric, but it shifts faster at the beginning and slows down as it moves toward the equator. From the phase lag, we found the speed of the activity shift is 19 meter per second square at the beginning of the solar cycle, and in 35 and 25 degree latitude belt, which is slowed down to 5.4 and further slowed down to 2.3 meter per second as the near the end phase of the cycle. But in southern hemisphere, this value first is faster, then it slows down and again increases. These findings are agree with those of Hathaway and Wright-May 2011 and Imada et al. The difference in the shift of activity may be due to the latitude dependence of flux emergence or cycle variation, difference in meridional flow velocity in northern and southern hemispheres. So these are references, and this work is accepted for the publication in Solar Physics. So this is the link for this paper. Please, I request you please go through this. Thank you.
Thank you, Pooja. Pooja is online. So if anybody wants to question, you can raise your hand. I see Tibendu. You can unmute yourselves.
Thanks, Shankar. So Pooja, this is, I'm happy to see so much work going on with the Kodaikanal Solar Observatory in terms of exploring the long-term archives of various groups now. So your work has some significance for the long-term behavior of the solar dynamo, and as well as the behavior of the small scale as the large scale dynamos, which need not be the same. So in this context, I wanted to know if you have tried to make some associations, deeper associations than what was presented with the solar cycle. You referred to a work by Hathaway and Reitmeier. I'm not sure in what context it is in, because they typically do surface flux transport models. But if we can just comment on that, it'd be nice.
Pooja, you can unmute and speak. Okay, I'm not seeing her unmuting. Okay, I think Divendra, you can put
Yeah,
your question in
I
the
will
chat.
include it in chat box.
Oh, thank you. Anyone else? If not, let's move on to the next one. Next talk is also going to be a YouTube streaming. Souvik Roy. Santosh, can you stream that second one?
Sure. Give me a minute.
Hello everyone, I'm Souvik Roy from CCISR Kolkata. I'm going to talk about magnetohydrodynamical understanding of the interactions between coronal mass ejection and Earth's magnetosphere. Let me give you an overview of this presentation. I'm going to talk about the physics of the star-planet interactions, the modeling of the flux ropes. I'll share some result and I'll conclude. We all know our star Sun has a vigorous magnetic activity, and because of that, it shapes Earth's magnetosphere. And we see auroras, we see space weather variations, we see geomagnetic storms, and it affects the satellites and the space missions. To prove the interactions between a star and planet, CC has developed a magnetohydrodynamical module based on Pluto architecture, where we have assumed that it's a far out Earth-like planet. It has an intrinsic dipolar magnetic field. The stellar wind or the solar wind in this case is a magnetized shock, and the domain is full of non-relativistic, compressible and adiabatic fluid of gamma 5 by 3, and the magnetic diffusivity is low but non-zero, so the magnetic Reynolds number is very high. Here in this video you can see how solar wind forces the Earth's magnetosphere. For more details about SESI star-planet interaction module, please see the references. Now let's move to CMEs. Other than the solar wind, the coronal mass ejections of the CMEs is the most energetic way the sun loses its energy into the heliosphere. And in this presentation, I am going to tell you about how we can model a ICME, and we can see the interactions between an ICME and Earth's magnetosphere. To model the interplanetary coronal mass ejection, that is the heliospheric counterpart of the coronal mass ejection, we have used a Goldwell flux rope model. The flux rope expansion is assumed to be negligible during the computation, and the flux rope central axis is assumed to be normal to the ecliptic plane, such that the core is passing through the Earth directly. Now it is clear that as ICME will see Earth in a shaped magnetosphere, so we have used the SESI SPIM to shape the magnetosphere first. And the output looks like this. Here you can see how the solar wind forcing creates a steady magnetosphere initially. Then ICME arrives and changes everything. If we can say that the solar wind forcing is creating a steady but dynamic magnetosphere, then we must have to admit that the ICME forcing is nothing but a perturbation to the steady state. And to understand that, here we are looking at the deformation of the magnetosphere in terms of magnetopause boundary. Magnetopause boundary is basically creates when the dynamic pressure of the incoming wind balances the magnetic pressure of the earth. Here you can see the noon, dusk and north polar view of the initial magnetopause boundary when the solar winds already created a steady magnetosphere. But as soon as the ICME hits, in the dusk view and the north polar view, you can see how the magnetopause boundary pushes back towards Earth. And in the noon view, you can see how the magnetopause boundary shapes with respect to the magnetic field orientation of the ICME. we have done a virtual satellite observation of the modeled ICME in our computational domain. A virtual satellite is nothing but a fixed point in space measuring the magnetic field with time. Similarly, like the wind spacecraft sitting at L1 point measuring the magnetic field intensities of the incoming ICME. Here I am presenting the observation of magnetic fields from wind spacecraft and a virtual satellite of a same ICME event. You can see the magnetic field correlates very much except for the X component, because in real case the ICME was not perpendicular to the ecliptic plane. To understand the effect of the ICME forcing on Earth's atmosphere in terms of mass loss and mass gain, we have taken a box of 10 RE around the Earth. On your left, you can see how the mass outflow rate from the 6 surfaces of this box depends on the time. The green curve shows how the wind, the solar wind, increases the mass outflow rate with time. And then the red curve and the blue dotted curve shows how it further increases for an ICME. The red curve is the twisted ICME profile, and the blue dotted curve is for an untwisted ICME profile. You can see for the untwisted ICME, the mass outflow rate is maximum and almost constant throughout the passage. But for the twisted ICME, the mass outflow rate is maximum only when the ICME core hits the Earth. This is because for an untwisted ICME, the reconnection on the day side of the Earth is happening throughout of the ICME's passage. But for a twisted ICME, the reconnection is maximum when the ICME core hits the Earth. That's why the mass outflow rate is also maximum when the core hits the Earth. On your right, this is the mass inflow rate with respect to time. You can see when the wind hits the Earth, it injects a plasma into the Earth atmosphere, but again the rate decreases with time until the ICME hits the Earth. For ICME, the mass injection remains throughout the passage, and it is almost 10 times than the wind. One of the key features to estimate the geoeffectiveness of an ICME is the measurement of DST index. The disturbance storm time index or DST index is a measure in the context of space weather. A negative DST value means that Earth's magnetic field is weakened. On the other hand, the ring current around Earth carried by the charged particles trapped in Earth's magnetosphere produces a magnetic field that is directly opposite to the Earth's magnetic field. So you can say a negative DST index means a weaker geomagnetic field, means a high ring current. Though we are dealing with fluids, not particles, still you can see in this top image that the fluid is following the drift and creating a ring current. Here the arrows basically represents the vector direction and the background color represents the vector amplitude. In the figure below, you can see the actual DST index and ring current correspond to a same ICME event. And both the images correlates very well. You can see the DST index suddenly decreases when the ICME hits, and at the end it increases and stayed in a steady value but different from the initial one. For ring current also you can see the current increases at the ICME hits and then again decreases and stays in a steady value but at a much higher value from the initial one. To understand the impact of the helicity of an ICME into Earth's magnetosphere, we have plotted the line profile of the current helicity density J dot B by B square along the X line, where Earth is situated at X is equals to 0. During the solar wind forcing, we have seen the current helicity density remaining 0 all over the X line, but as long as the ICME hits the Earth, we have seen that there is helicity injection into the magnetotail because of the ICME. ' Let me stop here with the conclusion that the in situ observations support CCSPM results and make it an important tool to probe and predict space weather conditions in future. The solar wind forcing leads to a steady and dynamic magnetosphere, and the ICME is nothing but a perturbation to the steady state. The dayside magnetopause is pushed further towards the Earth by the ICME, and it is deformed by the magnetic field orientations. The magnetic helicity of the flux flow distorts the shape of the magnetosphere and the magnetotail current system. The current enhancement around the Earth and the magnetotail is visible during the geostorm. The ICME comparatively enhances the in and outflow rate of the mass around the Earth. The mass loss rate is comparatively high when a twisted core is passing. The in situ DST index measurement correlates with the current enhancement inside the magnetopause, that is the ring current. The flux rods can inject the helicity in the magnetotail. Thank you all for listening.
Thank you, Souvik and Santosh for playing it up. Souvik is online. If anybody wants to ask him a question, you can raise your hand, please. Bhargav. Bhargav, you can unmute yourself and ask the question.
Can you hear me?
Yeah.
Yeah. Hi, Souvik. Very nice talk. I just, when you mentioned that by entering the CME, you actually changed the position of your magnetopause. So did you estimate how much is the change? Because you're mentioning that it's just a perturbation to the steady state obtained from solar wind. Did you estimate the change and basically how did you also vary the parameters of the ICME to kind of quantify the change and the parameter relation?
Yeah, Bhargav, so we are currently working on that, and basically I can tell you the values, but I don't have the plot right now.
No, it's okay. But what percentage does it change?
Earlier, I mean, in a steady state, it's like 10 RD, the magnetopause distance, standoff distance, and then when ICME hits, it becomes around 7 RD or 7.5 RD.
But okay, and how quickly it comes back, or it doesn't come back, or it stays there?
It comes back because see the whole part of the ICME, I mean since the magnetic field is helical, so in some cases it's parallel to the Earth's magnetic field, so the reconnection is not in the day side. Then the magnetopause comes back to the initial position, and sometimes on a higher value.
Okay. Good.
Okay, thank you. Dipendu, you can unmute yourself.
So I'm not going to ask a question, but I'm just going to throw it out to the community. And this is something that was not obvious to us when we began to do the simulations. But it looks like we can make an estimate of the actual ring current that has been induced due to the impact of a solar magnetic storm. And based on this, predict geomagnetic A index. So this is a very useful tool for modeling the space weather impact. And maybe with Bhargav, we would like to have a discussion on this to see, to explore the physics further and to kind of create a geomagnetic perturbation prediction tool as well using such modeling.
Okay, good. Okay, let's move on. The next talk is by Arghyadeep. Can you share your slides? This is also on solar wind effect on planetary atmospheres. Go ahead.
Can you see my screen?
Yes, please go ahead. Yeah.
Okay.
Good, that's right. Yeah, sure.
So, hello everyone. I am Arghyadeep and I'm a PhD student in the Department of Astronomy, Astrophysics and Space Engineering at IIT Indore. And I'm very glad to have been given this opportunity to speak at the 39th ASI meeting. The topic for my presentation is solar wind modeling and its interaction with planetary magnetospheres. And this work has been done in collaboration with Dr. Bhargav Vaidya at IIT Indore. So the term space weather generally refers to conditions on the sun, in the solar wind, and within the Earth's magnetosphere. This time-varying and highly dynamic system directly affects life on Earth due to the sun-Earth connection. There is a continuous flow of solar wind plasma from the sun to Earth, which composes the background solar wind. Disturbances and ejecta such as flares and CMEs propagate through this background solar wind and interacts with the Earth's magnetosphere. And then flux transfer events or FTEs facilitate the inflow of this solar wind plasma and energetic particles into the Earth's magnetic system by the process of magnetic reconnection. So it has been studied that almost 70% of the geomagnetic disturbances outside the solar maxima phase are not caused by flares or CMEs, but rather by the high-speed solar wind streams. And therefore, understanding and predicting the key properties of the ambient solar wind is crucial. And as a pilot study, we have compared various coronal and heliospheric models and have developed a background solar wind forecasting framework. This framework takes magnetogram data as input and through a series of extrapolations and physics-based modeling gives us the solar wind velocities at L1. This background model opens up the path for the investigation of much more complex phenomena such as CME propagation, CME-CME interactions, etc. And the work on this is currently in progress. The solar wind, after it reaches near Earth, interacts with the Earth's magnetosphere and forms certain regions of reversed magnetic field topology, which are prime locations for magnetic reconnection to occur. And as I have mentioned before, magnetic reconnection facilitates the inflow of the solar wind plasma into the Earth's magnetospheric system. And reconnection is very common at the polar cusps and the magnetopoles. It also takes place at the magnetotail, and it also often occurs in the presence of a velocity shear and even turbulence. This turbulence is important because due to the presence of this turbulence, it is also common that multiple current sheets form very close to each other, giving rise to multiple tearing modes of magnetic reconnection. The double tearing mode is a simplification of such a multi-current layer, and it is important from the perspective of fast magnetic reconnection. It is also beneficent to study such a system as it has a wide range of applications, which is not only limited to the magnetosphere, it can also be extended to solar flares and pulsar magnetospheres also. As I have touched upon before, reconnection in the magnetosphere often occurs in the presence of a velocity shear. In general, shear flow across the reconnection layer tends to suppress the reconnection rate. The theoretical scaling is given by the formula shown here in the middle. This scaling has been extensively verified in the context of resistive MHD, Hall MHD, and also particle and cell simulations. And it has also been found that this scaling holds true even during the plasmoid instability phase, which is an explosive phase of nonlinear growth dominated by multiple small plasmoids, which break the current sheet up into multiple segments. To study the scaling of the reconnection rate in the presence of shear for the double tearing mode, we solve a set of standard resistive MHD equations using the Pluto code for a double layered current sheet. Constant resistivity was set throughout the domain with a magnitude equal to 2 into 10 to the minus 5. And the initial magnetic field, the density and the velocity profile was prescribed to be of the form shown here on the right. These are double tan hyperbolic profiles, which give rise to two current sheets that are separated by a certain distance. In the bottom, you can see a snapshot of the density profile in the domain at t equal to 0, which is similar to a double Harris sheet-like profile. Here, you can see the movies corresponding to the time evolution of the system. The left panel is for 0 shear speed, and the right panel is for a shear speed of 0.75 times the alpha speed of the system. The colors here represent the out-of-plane current density J. The evolution shows an initial slow growth phase, which is followed by an explosive nonlinear growth phase. The explosive growth phase breaks down a portion of the current sheet into multiple small plasmoids. And throughout the evolution, these plasmoids are being continuously ejected from multiple X points. We observe plasmoid ejection along the outflow jets. We also observe plasmoid mergers, which eventually lead to the formation of larger and larger plasmoids, which then finally merge into the two largest magnetic islands in the system. The system on the right with the shear speed of 0.75 times the alpha speed of the system also evolves through similar phases, but this evolution is quite slower in time. This will be clearer when I show the magnetic energy curves in the next slide. Here, the left panel shows the evolution of the change in the magnetic and the kinetic energies for the case with zero shear. The purple curve shows the magnetic energy of the system. Please note that the magnetic energy is plotted as the initial energy minus the final energy, and thus the rising graph here actually translates to a decrease in the magnetic energy of the system. Both the profiles show a slow growth up to about t equal to 185, and then both the magnetic and the kinetic energy goes through an exponential phase. This is the time when the current sheet in the domain breaks down into multiple small plasmoids, and these plasmoids feed into the monster islands, thereby increasing its size. The panel on the right shows the time evolution of the change in the magnetic energy for different shear speeds. The red curve, that is for zero shear, is almost completely covered up by the blue curve, which is for shear of 0.25 times the alpha speed of the system. This means that the evolutions of these two systems are almost identical. The green curve is for a shear speed of 0.5 times the alpha speed, and the cyan curve represents the case with a shear speed of 0.75 times the alpha speed. As you can see, the distinct slow and explosive phases are visible for all the shear speeds considered in our study, but those phases are delayed in time by a certain amount. And after the explosive phase, the system relaxes into a relatively slower growth phase again, which can be seen by the flattening of the slopes of the magnetic energies at later times. So the plasmoid instability phase is a very interesting phase. In the 3D magnetospheric scenario, these plasmoids would translate to flux transfer events, or FTEs. And these plasmoids are continuously formed and are advected along the reconnection exhausts during the explosive phase of the reconnection. The panel on the top shows a portion of our simulation domain containing multiple plasmoids. And interestingly, one of the observational signatures of FTEs is a bipolar structure of the perpendicular component of the magnetic field. The bottom left panel here shows a FTE observation by the cluster spacecrafts. It shows this prominent bipolar structure. And by employing a virtual satellite in our domain, the trajectory of this satellite is shown by the dotted line on the top panel. By employing this virtual satellite, we are able to qualitatively produce such signatures along the plasmoid crossing. This is shown by the blue curve in the bottom right panel. One should note that the graph I have just shown here is just a qualitative approach, and a proper scaling of the values are required to directly compare any of the signatures with the observations. So another interesting result was the scaling of the reconnection rate. During the early slow growth phase of the evolution, the scaling of the reconnection rate obtained from the simulation had a very good match with the theoretical curve, as can be seen from this plot on the right. The red squares were the values obtained from the simulations, whereas the dashed line corresponds to the theoretical scaling, the one which I showed in a previous slide. But even though it has been shown that this scaling holds true for the plasmoid instability phase in a single current sheet in literature, we found that this scaling fails for the plasmoid instability phase for the case of a double tearing mode. As you can see by the plot on the right, for a later time in the evolution of the system, when the plasmoid instability phase has developed significantly, the scaling holds for very low shear speeds. But for the case with a shear speed of 0.5 times the alpha speed and 0.75 times the alpha speed, the values do not match at all with the theoretical curve. This is because for the case with low shear, the size of the primary large magnetic islands is much bigger. These leads to a feedback effect where the bulge of the magnetic islands tend to push magnetic field lines towards the X points, which are located directly above them. This results in kind of a feedback effect that strongly enhances the reconnection rate for the cases which have larger magnetic islands, and the cases which have larger magnetic islands are the cases with lower shear speeds. For higher shear speeds, the island half-widths are smaller because they have kind of a flattened structure during that time, and that doesn't result in that strong of a coupling between the layers.
3 more minutes.
Yes, thank you. I'm almost done. So to summarize, we have developed a data-driven background solar wind modeling framework using a combination of various empirical and physics-based models. We have investigated the dynamics and scaling of magnetic reconnection in the presence of a shear flow for a double tearing mode configuration, which can be treated as a ubiquitous phenomenon. And our results show that the theoretical scaling of the magnetic reconnection with a shear flow doesn't hold for the plasmoid instability phase of the double tearing mode. This is due to a structure-driven enhancement of the reconnection rate for lower shear speeds. We are currently in the process of analyzing the phenomena of particle acceleration in such system using test particles. The figure below is a glimpse of the same, where we can see a particle being trapped in a region with multiple plasmoids. The change in the color of the particle along its trajectory represents an increase in the energy. We have isolated various such high energy particles and have studied the effects of various mechanisms such as the island contraction, the electric field, and the plasmoid coalescence in the process of accelerating such charged particles. Our results show that for the phase of a plasmoid dominated fast reconnection, the particles produce an energy spectra which has a power law with an exponential tail at very high energies. That concludes my presentation. Thank you.
Thank you, Arghyadeep. Any questions? Please raise your hand. There is a question from Vaibhav. Vaibhav, you can unmute and ask. Vaibhav, we are not able to hear you.
Hello. Yeah. Am I audible now?
Yes.
Yeah. Hi. Thank you for the talk. Maybe I didn't get it. I'm just wondering how the solar wind is incorporated in your simulation, because your simulation largely concerned with the plasmoids, right?
Yes.
And currently, so where is the solar wind here?
So yeah, the presentation that I have just given, it is a combination of 2 parts. The first one is about the modeling of the solar wind. So that is the large scale simulation, how the solar wind is like the speed, the velocity of the solar wind basically. And then the second part is concerned with this small scale magnetic reconnection structure. These are not coupled in any way. Right now, it's just 2 separate phenomena that we are studying. But in the future, we plan to incorporate these effects of the solar wind in the magnetosphere from the context of magnetic reconnection.
Yeah, okay, thank you.
Yeah. Okay, there is a question from Dibedu. You can unmute.
Yeah, Arghyadeep, very nice talk. So I'm actually, quite excited here with the possibilities that your simulations of this plasmoid instabilities in the solar wind present. I have a belief that this plasmoids and the reconnection process associated with them can in fact also provide an alternative mechanism for driving the wind itself far away from the sun. This is something that has not been very seriously explored, I believe. Right now, we are doing some work in exploring switchback structures that have been observed by the Parker solar wind, and whether the reconnections that might be associated with the switchback structures could in fact accelerate the wind. I have a strong belief that in fact plasmoids can produce such switchback structures. I don't think this has been explored, but there is a ripe field here which we can talk about.
Yes, depending, of course. So during this plasmoid instability phase, you can see that the kinetic energy of the system highly increases. That means that the very strong outflow jets are produced. Yeah, that can be important from the perspective of acceleration of the wind, of course.
Yep, Bhargav, I hope you're there and you're listening. I think there is work to be done here.
Yes, absolutely. I don't know. Yeah, if I can hear it. Yeah. So I think, yeah, of course. I think the intention was to basically focus mostly on the plasmoids here. And then the idea was to couple, mainly to answer also Vaibhav's comment, because essentially we are targeting 2 separate things, but the idea is to couple at later stage. Maybe Dipankar has a question.
Okay, there is a question from Ankush. I will unmute him. Ankush, are you able to speak?
Yeah, can you hear me?
Yes,
Yes,
yes.
Sankash.
Yeah, so I have a question on this. What is the distribution of these FTs do you observe after reconnection? And have you seen any like expanding FT moving?
And so you mean the size distribution?
Because, yeah, size distribution.
So we have
Because
not
still,
yet. Yeah, please go on.
yeah, so that is one of the important question. I think we don't understand what is exact FT distribution and even whether they expand or not when they are moving across the magnetosphere.
So we have not yet explored the size
That part.
distribution of the FTs as soon as they form. But to answer a part of your question, we have observed that these small plasmoids, they coalesce to form larger and larger plasmoids. So as time increases, there will be newer plasmoids that are forming, which are eventually merging into the larger plasmoids than that. And even afterwards, they will be merging with the even larger magnetic islands.
Okay, thank you.
Okay.
From Dipankar.
Yeah, can you hear me?
Yes,
Yeah.
yes, sir. Go ahead.
Yeah, thanks. I have two comments. One is this plasmoid. Have you done any statistics in terms of the sizes and velocities and all that? Why I'm asking this, Ritesh and Vaibhav has done some observational work from current sheets and these plasmoid, their direct observations. So it could be quite interesting to see whether they form any kind of, scaling laws or so on. So they can be related with some more physical insight.
Yes, Dipankar, currently we have not done any size scaling like the statistical distribution of the size of the plasmoids, but yeah, of course we can explore that.
Yeah, because there are some observational, signatures of different sizes and so on.
Yes,
So,
that would be quite interesting.
Yeah.
Yes.
The other comment I have is, since you mentioned about the particle acceleration perspective, so are you, I mean, I know it's very tough, but are you planning to include PIC and have a hybrid model at some stage?
We might get into that, but right now, currently, we are just using test particles to see how the field accelerates the particles.
Yeah, because for the future, I think eventually we have to get there.
Yes.
I'm sure Bindu and Bhargav will be knowing this. If you
Yes.
could include the MHD and the PIC code and sort of have a hybrid model at some stage, that will be.
বাংলায় বলে খেতে পেলে শুতে চাই.
I understood that also in Bengali.
It might take to develop that kind of stuff. I mean, of course, we all want to do that.
No, actually, I just would like to put one comment here to Dipankar. I mean to say, you see, when we do simulations in the MHD scale, there is a restriction on the scale that we can go up to study particle acceleration. And hybrid models, when people do, they can only go up to proton scales. Because if you're interested in electrons, you actually have to go from the PIC approach. So it's an extremely difficult problem. That is what I was also alluding to in my earlier talk in Aditya L1 workship.
Right. And
If
as a
you want,
modeler,
yeah.
Go ahead, complete, Bhargav, complete.
No. So basically, if I think the best approach would be to have PIC in a very small region where you want to only understand electron acceleration and have a background of this thing, but you cannot evolve both together. It will be extremely difficult.
I mean, it's the next step. You say the Leuven group is still trying to do it last 10 years. I know.
Yes, and yeah, I know it's super difficult, super difficult.
Can I step in here? I think, I mean, the discussion is going more detailed. So maybe you can have it after the next talk if you want to go for a more detailed discussions. Okay.
Sure.
Thank you, Arghyadeep. And can you unshare your slides?
Yes, of course. Thank you.
Can I ask my
We are already running out of time. Muthu, can you share your slides?
Yes, sir.
Yeah. Yeah, please go ahead.
Yes, sir. Hello, good evening to all. I am Muthu from Indian Institute of Astrophysics. Today, my talk is about periodic and quasi-periodic variations in the calcium K index during the 20th century using Kodaikanal data. And this work has been done with Professor Jagdev Singh and Dr. Ravindra. At Kodaikanal Observatory, we have 4 types of historic data. One is calcium K line spectroheliograms from 1904 to 2007. and white light photoheliograms from 1904 to, and they're observing, I think, maybe till date, and H alpha spectroheliograms from 1904-1999, and prominent spectroheliograms at K line. And the numbers which I have given in bracket is the total number of images available in each data sets. And my study is mostly concentrated on this calcium K spectroheliograms data, which is available from 1904 to 2007. And this is the instruments used for observing the images at calcium K line. And this is a cytostat image, and this is the spectroheliograph. And this design of the spectroheliograph was specified by George Ellery Helle. It images the sun in calcium K line at 3933 angstrom with a passband of 0.5 angstrom. And the unique feature is the same optical setup is used for the whole 100 years of data to observe. And this is the digitizer unit used for digitizing the calcium K photographic plates. And these are the components of digitizer. And there's a 1 meter lab sphere with exit port of 35 centimeter, and the uniformity of light is 1% from center to limb. And this is a current controlled stabilized intensity source. And imaging lens have a less negligible vignetting, and it's a 4K by 4K CCD camera. Pixel size is of about 15 micron, and it is 16-bit readout. And the temperature of operation is 100 degree minus 100 degree centigrade. This is the image of our digitizer setup available at Kodaikanal. First one is 4K by 4K CCD camera, and this is a photographic plate holder, and this is a lab sphere, and this is a data acquisition system. This is a sample digitized image. This was taken at 1958 January 20th image, and this represents the North Pole and South Pole markings on the digitized image. So these are the calibration and analysis procedure we have adapted to analyze these calcium K spectroheliograms data. And in our previous article in 2014 and 2017, we have described the flat fielding correction and density to intensity conversion and limb darkening correction and instrumental effect correction. And then we identified the active features of plagiars, networks, etc. But we found still some remnant instrument intensity vignetting to correct for it. So we have developed a new methodology to correct for this remnant intensity vignetting and made the background more flattened. This has been done by Priyal et al. In 2019. And then we separated the image into two categories, good and okay data, based on their intensity distribution. I will explain details in the further slides. Then we identified the active regions and found the periodicity and quasi-periodicities in the whole 100 years of data. So this is the method to make the background more uniform. We segmented each analyzed image into 10 circular zones of equal area, and each zone we divided into 8 zones of 45 degree having equal area of solar image. Then using the intensity distribution in each segment, we replaced the 35% of high intensity points by the peak value of intensity distribution in that segment. Then we smoothed that resultant image by 8 by 8 box-care average, and we generated the background smoothed image on the sun. Then we divide this background image from the original image that yield the image corrected for the instrumental effects. Then the new images were normalized by the average value of 25 pixels around the peak value, and it showed a significant improvement over the earlier analyzed images. So this is the way we classify the images as a good and okay images based on their intensity distribution. And the top row that shows the normal contrast image means the images are taken at the calcium K line center showed the normal contrast image. Like in the middle row, which shows the very narrow intensity distribution that represents the very low contrast image. This may be taken, probably taken in the off band of calcium K wavelength or during the presence of high clouds. Actually, in the spectroheliograph, in the slit and the top and bottom portion of the slit, there will be a window where the observer have to manually adjust the slit position center around the calcium K3 line. So some observer may mismatch that alignment that may leads to the low contrast and high contrast image. This has taken during the maximum phase, but even we have a very low contrast image. The bottom panel is taken in the minimum phase of the solar cycle, but it has a very broad intensity distribution. So this we classified as a high contrast image. These images are mostly likely taken in the blue wing near the K2V emission peak of the calcium K line. So with this intensity distribution, we classified as good and okay images. And this is the number of images available of good data, okay data high contrast, and okay data low contrast. And after 1975, there is a number of images are very less because of the scarcity of photographic plates and also very less clear sky conditions over these periods. And also that from the instrumental setup that the images have some dark lines that have come up. So after 1986, the instrument has been cleaned and it is aligned properly. Then the number of good images have increased considerably, but still the number of images after 1975 is less compared to those previous years. And this period 1942 to 1948, the low contrast images are high. This may be the observer has taken the images off from the calcium K3 line. So these periods we have a low contrast images more. So we restricted our analysis from 1905 to 1984 because of very less number of good images after that. So this is the variation of full width of maximum. From the intensity distribution of each image, we have calculated the full width of maximum for good and okay data. And this top panel shows the full width of maximum variation of the good data, daily data, and overplotted with the yearly average. And bottom one for the okay data. The variation in the full width of maximum of the intensity distribution can be because of changes in the emulsion or different methodology to develop the photographic plates or different observers who used to center the calcium K line on the exit slit visually. So this full width of maximum actually represents the quiescent chromosphere. So it should not vary much, but this variation may be due to because of these conditions. So this variation in the full width of maximum, in other words, the contrast of the images can affect the observed amplitude of large-scale solar activity represented by plages, but it may be probably by a small amount, but it can affect the detection of various network features by a large amount. So in this work, we have restricted our analysis to study only the plages. These network features we have not analyzed to study the periodicities and quasi-periodicities. But in a recent paper, which was accepted in 2020 by Singh and Priyal et al., we have overcome this full width of maximum variations, and we have not changed the contrast of the image by our new technique, and we brought down the full width of maximum variation to be very less amount. And then we have analyzed this network features periodicities also that has been described in this recent paper. And these two separate things is because of the low contrast and high contrast image of the OK data. So this is the histogram. From the good data, full width of maximum shows the intensity distribution vary from 0.05 to 0.15 and peak value is around 0.08. For OK data, it is varies from 0.035 to 0.2 and the image peak is around 0.05 for low contrast and 0.12 for high contrast. So it may be noted that full width of maximum of the distribution in the number of OK images is similar to that of the good images. This is because of flaws in the image due to the photographic emulsion, passing clouds, or number of dark lines which cannot be corrected by the adopted procedure. This implies that just putting the limits on the full width of maximum of the intensity distribution, we cannot select good and okay images. So we need to visually inspect the intensity distribution of the and the image quality after analyzing the images to term them as good and okay. So we visually inspected each image intensity distribution and then we classified as good and okay data. We have not go with the full width of maximum limits. And this is the variation of the averaged intensity over the whole sun with the time, and we plotted against a sunspot number. This is for good data, and bottom one is for okay data with monthly data overplotted. Here in okay data, we had a large scatter due to this bad quality or non-uniformity of the data. Good data show considerably good correlation with the sunspot number, except this period where we have a less number of images during this period that shows the less activity compared to the sunspot number. Then in each image, we have identified the active region features as Pooja said already. We have classified the active region features as a plage, enhanced network, active network, and quiet network. And this is the identified plages. Plages, we have given the intensity threshold, which is greater than 1.3, and area threshold. Okay, sir. An area threshold is greater than 0.5, and enhanced network is 1.3, and area is about 25 arcsecond square, and active network between 1.2 to 1.3. So these are the criteria we are given to identify the active region features. And this shows the row profile of this particular line after correcting for limb darkening correction and intensity vignetting instrumental effect. And this is the plage area variation with the time for good data. And this is for OK data. As we mentioned, there is a large scatter in the OK data. And this is the scatter plot of average intensity of Kodaikanal data. This is plage area of Mount Wilson data and Talto. Talto et al. Have used the Kodaikanal data with the which is digitized with the 8-bit scanner, and they have manually picked up the plages and even Mount Wilson Observatory also. Then we compared their plage areas with our average intensity, and we found the correlation with the Mount Wilson data of 0.6 and with Alto of 0.72. Here we could see the two branches of this scatter plot. This this shows the two branches of plots. This shows that even at the greater average intensity, there is a less plage area. This is due to the large contrast of the image. This may be due to the installation and alignment of the spectroheliograph at the beginning of the 5 years when they started analyzing the calcium K spectroheliograms. So we separated these branches and we found the good correlation with 1915 to 1984 of 0.84. And then we did a power spectrum analysis to study the periodicities. It shows the variation in calcium K intensity with periods of 24 years and 10 years and 3 years in both good and okay data sets. This periodicities of 24 and 10 years represents a well-known 22 magnetic cycle and 11 years solar cycle. The period of around 3 years may be due to the duration of a large number of active regions around the maximum phase of the solar cycle. And there is a period around 1.1 year in the OK data. This may be due to the seasonal variations related to seasonal conditions. And we have done the wavelet analysis to study the periodic and quasi-periodic variations. And this is for the good data. This also shows the 24 years, 10 years, and 3 years periodicities for both the good and OK data. This is for good data and this is for OK data. And here in OK data, we had a 57-year periodicities, but since we have only 100 years of data, so this we cannot be reliable. And we have applied a low pass filter to study the quasi-periodicities. We split the data into two intervals, 50-50 years, use a low frequency filters to study the variations with period less than 9 years. So this analysis shows the quasi-periodicities of 7.5 years and 3 years in both the data subsets. The quasi-periodicity of 3 years appears to have relatively more power in the active phase of the solar cycle. And here it is showing the less power, maybe due to the non-uniformity of the data. And the 7.4 and 8 years is a part of the 10 years periodicities of solar cycle.
One
And
more minute.
okay, data. So the conclusion is it is very important to know the amplitude of the variation of previous solar cycle accurately for the prediction of strength of the next or future solar cycle. So it is essential that all the calcium K images are properly analyzed, free from instrumental vignetting, normalized, and selected to generate a uniform time series of images for further analysis. By getting a very good correlation between the different data sets on daily basis from different observatories, it will be possible to combine the different data sets and predict the future cycle reliably. It may be noted that at present, the correlation between the different data sets shown by Toltov, Ermoli, Berthelot, and Chatterjee, all they have shown the averaging the data over months and years. So we should go for uh, daily correlations. Therefore, we suggest that all the images from different observatories should be analyzed uniformly with a common methodology such as the one adapted by us, and then combined with some factor depending on the characteristics of the instrument used to generate uniform series with less data gaps. This methodology has been detailedly explained in our recent paper accepted in ABJ. So with this, I finish my talk.
Thank you, Muthu.
Thank you, sir.
There's one question by Ritesh. Ritesh, you can unmute and answer.
Okay. Hi, Muthu. I
Hi.
have a basic question from the starting part when you showed different contrast images. So
Yeah.
did you apply some techniques like contrast stretching or histogram equalization? Yeah, this slide.
That we have done in our recent paper. In this work, we have just visually inspected the each intensity histograms and classified it. But in our recent article, we have normalized the images with respect to the full width of maximum, and then we classified images as good and okay, which shows the good correlation on daily basis with the different observatory data also.
No, what I am telling is like those techniques are actually to increase the width of your intensity band so as to cover it completely.
Oh.
So because if that were done, so maybe some low contrast image could have
Low
caught.
contrast image, yeah, we have to increase that
Yeah.
width, and the high contrast, we have to reduce the width.
Mm.
So that
Because later
adjustments.
visually you had to anyway classify it, so this could have been I don't know, like done that time.
In our recent paper, we have done that actually.
Oh no, that is normalization. I am talking about contrast stretching. That is
Contrast
like
stretching we
based
have
on.
done actually.
Okay.
If the full width of maximum within this particular limits, like 0.1 to 0.11, then we have gone in the steps of, we are given the gamma value like image to the power gamma. So we have increased the gamma or decreased the gamma value to bring the images within that full width of maximum limit. So we made it uniform.
Yeah, that is gamma correction actually.
Yeah.
Anyway, fine.
Okay, there is one more question from Mahendra. You can unmute and speak.
How you calculated the quiet network actually? How you segregated it means quiet network?
With the intensity limits and if the intensity is between 1.1 to 1.2, then we classify it as the quiet network.
Okay.
Okay, thank you, Muthu Priyal, and I thank
Thank
all
you,
the
sir.
speakers in this session, and special thanks to Santosh for playing those two videos. We will close the session now, and I think there is a final session at 3:30 for the final session of the ASI. Santosh, you have any announcement from the workshop organizers?
No, I don't have any announcement.
Okay, okay. Then I think you guys can quickly pick up your tea and then come for the final session. Thank you.
Thank you all.
Thank you, everybody. I think we had a great session. Thanks.
Thank you.